Hi, I'm Ellen Kowalczyk. I'm a member of the review board here at Black Hat, and I'm very excited today to introduce Alex Ketchilian and Ellie Beerstein from Google. Google has a unique challenge when it comes to insider threat. With over 180,000 employees and a culture of creativity, of research, of experimentation, and so I'm excited to see the research that they have done and how we can use it in our own environments. So welcome, Alex and Ellie.
Bonjour, my name is Eli, and this is Alex, and we both work on research at Google. And today, we are really excited to talk about one of our flagship systems called Facade, which is an anomaly detection system we use to detect insider risk at Google. Before getting started, if you would like to have a copy of the slide, you can head to that URL or use your QR code to download the slide so you can follow along. We will show the QR code at the end of the talk as well, so you can review the slide at your own time. With that out of the way, let's get started. At Google, we process over 10 billion events every year to try to find insider threats which target Google and Alphabet in general. What we call insider threat can be broken down into three types of potential risk. The first one is what we call intentional insider threat, which is a rogue employee trying to access and exfiltrate, for example, some of our data. An unwilling employee which has been deceived or is coerced into performing an attack against Alphabet. And last but not least, we also have accidental insider threat, which are employees who are well-meaning, but for example, might decide to do an action which is putting Alphabet at risk. Here's a few concrete examples of the type of threat we see, so we're all on the same page. For intentional, we can have access of confidential documents without business justifications through access permission abuse. So it's not a secret. Google uses Workspace to share our data. We use Google Slides, Google Docs, and so forth. And sometimes people share documents to a broader or too broad of a group. So you could imagine an insider attacker trying to exploit some of the sharing it has to access documents it's not supposed to, and further out, exfiltrate some of our trade secrets. That is an intentional abuse of the permission. Unwilling, it happens sometimes that some of our employees are compromised with malware, and then the malware is used to exploit the access of the unwilling employee to access some of the data and, again, cause harm to Alphabet. And last but not least, we have employees who want to share data with a partner and didn't realize the partner is not under NDA or are sharing it to a way which is not approved and put some of our proprietary data at risk. So those are some examples of what we do call insider risk. So that's what we try to detect. Now, why is detecting insider risk so difficult? The first thing is insider risk is extremely low incidence. As I mentioned, we have billions of events every year from people accessing different documents, doing some SQL queries, looking at some access control. And we are literally trying to find the very few events which are suspicious that we can investigate and our investigation team can look at to detect potential threat. The second problem is two employees doing the same action have very different results. If one employee is actually working on a special project, it is absolutely normal to access sensitive document. If the employee is on a completely unrelated organization and accessing the same document, that is a problem because it has no business reason to access it. So there is no specific pattern to look for into the logs. There is no specific exploit signature to look out for because it's all about context. And the last but not least, those are people who are employed by Alphabet, so they already have access. We're not trying to prevent them to have access. They are supposed to have access. The problem is by giving access to a bunch of tools and a bunch of documents, we have a very wide attack surface for each employee, and we try to figure out how to detect those things when legitimate credential and legitimate tool are used. And so that I hope explain why insider risk is such a difficult and different type of detection you need rather compared to traditional intrusion detection system. And so since 2018, actually Alex had the idea in 2016 and it took 2 years to initiate the project, we were working on Facade. And so Facade is a high precision, which means it has very, very low false positive alert because we don't want to have alert fatigue. We are rather optimizing for being sure rather than to do as much as we can, which use deep learning, so TensorFlow specifically, we use TensorFlow to do it. Contextual, meaning that we take into context who is the user and what is the resource access, and Alex will tell you how we do that later in the talk, to perform anomaly detection, which is trying to predict whether or not this user accessing that resources is normal or not. And that is what Facade is trying to do. And one of the interesting things when we started to talk about Facade externally, a lot of people told us, well, you know, anomaly detection has been tried again and again, and no one can make it to work. So there is a lot of paper in the academic settings which says anomaly detection doesn't work. So the reality is we think Facade works because we work at a very, very, very large scale. As I mentioned, we're working at a billion scale. We don't think anomaly detection works at a small scale. So bear that in mind when we're going to talk about the open source implementation that we are releasing today. We don't expect it to work out of the box, and we don't expect it to work on small data sets. That is not what anomaly detection is. It's for like very, very large scale data set. So how good is it? Well, without spoiling what Alex is going to tell you, we run a bunch of red team attack, and in many cases, Facade is able to detect the red team as a 0.01% most suspicious event, which means that with very, very few investigation of events, we're able to catch red teams. And those are tests we perform on tens of millions of events. Again, the scale is important here is literally finding a needle in a haystack in a very, very accurate way. So the investigation team only have to look at a very, very few percentage. So Alex will tell you a little bit more at the end of the talk on how we evaluate that in detail. But this is to give you confidence that what we're going to talk about is actually doable. It requires quite a bit of personalization and fidgeting to make sure that it works for your use case, but you can absolutely get there. So today, what we're going to do is I'm going to give you a brief overview of how Facade works. Then Alex will tell you how we convert resources and user into a dense embeddings to represent them. Then we're going to tell you how we use the system to score anomalies across various time period. And then Alex will finish by telling you how it is used in practice and how we find attackers and so forth. So by the end of the talk, you should be able, with the open sourcing, to adapt it to your own use case. So Facade, how Facade works? Well, the problem formulation we use is it normal for a given user to access a given resources? So let me give you a practical example. We have, for example, a hardware division at Google, which works on TPU, Pixel phone, and so forth. And this division is supposed to access TPU schematics. It is normal for our hardware designer to access the schematics of the TPU as base of their role. Now, if we have a rogue actor, which let's say works as ad sales and start to access a TPU schematic that is extremely suspicious, why would an ad sales person access for business reason a TPU schematic? Of course, this is a very contrived example and probably the most extreme, but it's to highlight that depending on what the document is and what the user is, some patterns are totally fine and some patterns are clearly abnormal. And what we try to say is Facade needs to predict that the second one is really abnormal and the first one is absolutely normal. And that's what we try to do with the system. So how does it work in practice? Well, we have a user embedding, which is a dense representation of what is the user, what is his role, which organization it belongs to, what group does it have access, and so forth. And then we have a resource embedding, and the resource embedding is what is the access pattern for a given document, but also can be a query of SQL, can be access to a table, can be access control. We do that for many, many things. And Alex will explain to you how to do it for any type of resources that you would like. That's why we say you have to adapt the system for your own needs. Depending on how your logs are structured and the type of event you have to adapt. And then we feed that to a TensorFlow model. And the TensorFlow model returns a single score, which is an anomaly score. If the score is close to 0, it's fine. If the score is close to 1, well, it's very, very abnormal. And the idea is we rank for every time period by that score, and the one who has the highest score are the ones which are investigated for potential insider risk. So that's the base, that's the gist of how Facade works. The thing is, one of the tricks and one of the things which actually makes the whole thing work and is the least known, we believe, is how do we train such a system when we literally have so few examples of insider risk. Usually when you have a machine learning system, it is assumed that you're going to have, let's say for the Gmail classifiers that we work on, a lot of spam and a lot of ham messages, and you try to balance the data set, and the model learns from creating a boundary between good and bad email. For insider risk, as I mentioned, we don't have that. We have very few incidents, and we have a vast amount of normal events. So how do we do this? The answer is we actually do not use at all any insider risk information. We only train with a very neat trick that I'm going to explain. We start by computing for all the activity we have, the two embeddings which are normal embeddings. So for example, we would compute for the user of the hardware division their embedding and the embedding of the TPU document. And then if we have someone from DeepMind who work on Alpha Secret, our new secret model, we're going to have the user B embedding, and then we have Alpha Secret doc embedding. So we have two different embeddings, and those are completely normal. Then, when we try to train, what we do is we start to create a data set of those normal embeddings, so group of twos, right? And then we swap. So we start to say, OK, now the user B is going to access a TPU document that is not normal, and B, the user A is accessing the Alpha Secret document, which is not normal either. So basically, we create anomalies by swapping the embeddings. And that way, we can create an almost infinite data set by balancing that out. So that's how it works in practice. That was basically the core ideas that you need to remind, to build an understanding of what Facade is, which is we use anomaly detection by contrasting the user embedding with the resource embedding and try to predict the score, which is used to run the event. And the way we train is by basically at training time mixing and matching embeddings so that we create a balanced data set that we fit to the machine learning. Now, what Alex is going to do is going to go and give you way more detail on how we create those embeddings so you can reproduce the same. Alex?
Thanks, Eli. So that's the theoretical framework for Facade and what we're trying to achieve. So let's dive into the details and what it means to have a user embedding and a resource embedding and everything else that follows. So we have to start by first representing these entities in the system. So we have to talk about featurizations. So I'm going to start with the resources. So let's have some shared understanding on what we're trying to do here with the resources. The first thing is that whatever method we developed must handle a very large scale, heterogeneous set of resources. So we're talking here about billions of distinct items. And the types of those items is quite different. We have documents, we have spreadsheets, video, data tables, RPC endpoints, URLs, etc. Any type of resource, corp resource that you have that you want to protect, we want the system to be able to operate on it. So that's already going to create a challenge here for content-based features. So one thing we don't want to do is spend a lot of development time on a case-by-case basis for each resource type. And then if we do that, if we have made that choice, then we'll have to have large maintenance cost as well. And on top of that, it's quite computationally expensive at inference time, in particular for multimedia type of resources as well. The other issue here is that in a corporate environment, there's a large distribution shift and drift with time. So new resources appear constantly, like people create documents, people create spreadsheets, etc. every day. And the system needs to be able to handle that without requiring a very long retraining. There's also a very, at some point philosophical, but still inherent difficulty in predicting the appearance of novel topics. in the content. So this is a problem we don't want to have in the system. So let's see how we do, how Facade deals with those problems. So I'm going to give you a piece of intuition here that will, I think, help build the case for our featurization. So let's say we lived in a perfect world, on a very simplified world, where the set of resources is small, is constant, and the meaning of each resource is also stable in time. There would not be any problem here, because you would just be able to featurize each resources as categorical features, essentially. This is, however, not the case. Like, all of these three constraints are violated in practice. So the main intuition here is to project the resources into a more stable set of similarly opaque identifiers. And a good stable set here in a corporate environment is the set of user IDs or users. And I'll give you a few examples of that. So this gives rise to what we call history-based featurization for our resources. And a history-based featurization is simply a bag of words of the user IDs who have previously accessed a given resource. So now I'll give an example of this. So here you have a document. Let's say we're looking at document resources, and you have its access history from the logs. So the document is first created by user A, then accessed by B, C, D, and A again. So what Facade does is that it computes the feature of the document in given time periods between accesses. And for every given time period, the feature of the document, the featurization of the document, is just the bag of words that corresponds to the previous set of users who have accessed the document. So for the first time period, when the document is created by user A, it's simply represented by A's user ID. For the second time period, it's the set of two elements, A and B, then ABC, then ABCD, and then again ABCD. It's just a set. So this is a little bit of a simplified picture of what we're doing, because in practice we use weights and other features on those accesses, but this is really the core idea for representing resources. So as Ellie mentioned, we're also releasing a reference implementation, and I want to show you how easy it is in the reference implementation to represent such a resource, such an access event. So basically, you have a few fields. You have a timestamp, obviously. You have the principal that's accessing the resource, and you have the type of the resource. This is just for internal bookkeeping. And finally, you have the resource ID. So this is simply an opaque identifier that allows you to identify the document across time or the resource across time. And the only thing you have to do in the Facade framework is specify the resource ID and create those records of access. And Facade will take care of the rest. Facade will take care of the history-based featurization of the document through time. So at this point, you might have a different question. OK, now we have this set of user IDs. How do we go from that set of user IDs to a dense vector representation of the document? So let's go through that. So somewhere, we're going to learn a dense matrix of embeddings. So every row in this matrix represents the embedding of a given user. And every column is a dimension of the embedding. So this is all learned. This is part of the TensorFlow model. So to create the first step that we're going to do to create the embedding that corresponds to that particular resource at that particular time is to fetch the user ID's embeddings from that embedding matrix and gather them, and finally sum them together. And there's a little bit of a normalization step that I'm removing here, but this is essentially how you get to a dense representation of the resource. You simply sum together the embeddings of the users that have previously accessed the resource. All right, so let's look at what we do for featurizing users, because as you remember, Facade is a two-part system. We have the embedding of the user and the resource. All right. So there's, generally speaking, two types of user attributes. The first type is relatively easy to deal with. These are low cardinality and stable features, things that, for example, job titles. For example, in any given company, there's usually a very small, finite number of job titles you can have. So here, there's no problem. You can really use a direct categorical featurization. What is more interesting and more powerful for a system like Facade is the high cardinality and unstable attributes. So things like team assignments, project assignments, meetings that people attend together, pull requests that are reviewed, like code reviews, etc. And those are particularly tricky to deal with because there are large distribution drifts. For example, every time the company is reorged, people might change teams. There's new projects that come up. You have to be able to deal with new employees being onboarded. So for that, our solution is to use implicit social networks. So this is an example of how it would work for, let's say, user A, who is part of projects assigned on a given project here. So in order to do this, Facade is going to internally expand, is going to get the list of everybody else who's assigned on the same project at that given time. So here we have B, C, and D, who are assigned to project XYZ. And I think at this point you guessed it, the project feature for user A is going to be the bag of words that corresponds to the user IDs of B, C, and D. So user A, the project feature for user A will simply be B, C, and D, just a set as previously. So if we generalize this a little bit, in the Facade system, any user is featurized by a set of sets of other user IDs. It's a bit of a mouthful, but it's just sets all the way down. And we have one set per attribute type. So sets for teams, sets for projects, sets for department, etc. And this is how it would look like in the reference implementation. It's a complex explanation in some ways, but it's a very simple implementation and a simple way to use it. So here, it's even simpler than the resource. You have the name of the complex attribute, for example, the project attribute here, and then you have the value. And that's the only thing you have to specify. Obviously, the principal and the timestamp, the validity timestamp for this description of the user. And Facade will take care of the rest for you. Facade will compute those sets, those weighted sets in practice, and compute the subsequent dense embeddings. So here's a quick example of how that would work. This is a very simple example. Again, we just have 3 features that represent the user. We have a job title, we have a team set, and we have a project set. So we embed each of these. The top one is easy, it's just a categorical feature. The bottom 2 are embedded using the same method that you saw previously. And then we feed those embeddings to an intermediary model, a submodel, a subnetwork. And that constructs the user embedding. So you can see here, based on this picture, if you generalize a bit the set of user descriptions, you can see that we can have very fine-grained, very detailed descriptions of users. Really, it's quite a flexible system, and you can put a lot of features in there if you wanted to. So here are the key takeaways for our featurization of users and resources. So first, the first thing to notice is that the featurization methods are universal. They are meant to work easily across resource types and user types, and in some ways, like company structures as well. They are robust to distribution shift because the set of user IDs in a corporate environment does not change that fast, essentially. They naturally handle new resources and new users without you needing to retrain the underlying TensorFlow models. Essentially, you have offloaded the problem of computing the problem of updating the model to a problem of computing fresh features for users and resources. And finally, and importantly, because we want to do this at scale, those featurizations are extremely fast and therefore extremely efficient to implement. All right, so at this point, I've only described point-wise scoring, but in reality, as security practitioners, you need more than that. You need scores that pertain to entities across time, to users across time. So this is what we have currently. So let's say our user is accessing all these different resources, a presentation, some multimedia, a document, a website, etc. And what we have now is a system that gives you single access scores for each of these accesses. So that's good. You can already answer questions like, what is the most anomalous resource for this particular resource access for this given user? Or what is the most anomalous resource access globally across all users? These are interesting and important questions. But in practice, we also need to answer the question of, for this particular user and this particular activity set that represents maybe like one day of actions, what would be the score? What would be the anomaly score of all these accesses considered together? OK, so I'm going to go through a few attempts at designing a reasonable way to aggregate those scores, and then we're going to see the issues here. So the first thing we might think of is, well, let's just average the scores. We have all the scores. We just sum them, and we divide by the number of accesses. So that's going to be very problematic, because that would allow an attacker to hide their malicious actions, their malicious accesses, by performing a large volume of good accesses or low-scoring accesses. OK, so averages out. OK, well, let's not divide, and let's just sum the scores together. In that case, we're going to have another bias, which is that users that perform more actions will tend to be more anomalous. OK, that's also out of the window. Well, there's not that many aggregation operations we can have mathematically on a set of numbers, so the other one is basically the maximum. The problem with the maximum is that, obviously, it ignores all but one access. So this is also quite suboptimal, but not as bad in some ways as the previous two. So instead, this is what we do. There's actually multiple ways of combining scores together and embeddings together, but this is one way to do it. It's a two-step process. In the first step, we cluster similarly anomalous accesses together. I'm going to go into a little bit more details of what that means. And in the second step, we look at each cluster, and we give each cluster one score, which will be basically the maximum score within that access cluster. And then we sum all the maximum scores together. So this is the rationale here. We cluster to eliminate redundant and repetitive anomalies. So in many, many cases, accesses are correlated, and we want to, in some ways, like decorrelate the accesses. We're going to use the embeddings that we've already calculated for the resources to compute those similarities between resource accesses. We use the sum operator so that we get higher scores for activity sets that have more diversity in their anomalousness. And finally, we also use the maximum operator within a cluster to prevent attackers from decreasing their scores. So here's an example of how this would work. Again, we have the same user, we have the same activity. So I'm going to represent the space of embeddings as a 2D flat representation here for pictorial purposes. So the first thing we do is here I'm just going to represent the embeddings that we've computed for each of these documents into the same space. So you get that for free in the Facade system, in the Facade framework. Like embeddings are the first step before calculating the, or the second to last step, I would say, before calculating the scores. All right, great. So you can already see that some resources, for example, the presentation and the documents, lie together, close in space. So that means that essentially, from the model's perspective, these things are quite similar. They represent quite a similar type of activity from the user. Similarly for the internal web resource and the video. So we're going to apply a generic clustering algorithm on these, and we're going to get 3 clusters. Here, the clusters are well-formed. And so these 3 clusters represent essentially the type of activity of the user, but with deduplication. So looking at the high level, you can forget all of the times like the user basically has exhibited these 3 types of actions, these 3 types of activities in their scoring period. So to compute the overall score, you're going to take the maximum score in each cluster and sum it together. So for example, for cluster 1, the max score is the access to the PowerPoint document, and that's 0.23 here. And you're going to repeat that for all clusters. So in doing so, you can be pretty sure that an attacker cannot decrease their score, but also you remove potentially redundant malicious activity. All right. So the most important part of any work that deals with security in some ways is evaluation. So to evaluate that, we are using a red team, so volunteers, essentially, who would simulate insider attacks. And before I get into that, I want to tell you a little bit more about the scenarios that we have. So if you look at the Facade paper that's on archive, there are more details there. But I just want to give you a sense of the type of playbooks and scenarios that we've included into that evaluation. So the first scenario is we call it the media sharing platform scenario, where an attacker seeks information about the inner workings of the platform, obviously in this case YouTube. This information could include like corporate financial data, the earnings about individual creators, or the ranking algorithms that are being used, for example. So another red team scenario is what we call the hardware product scenario. In this case, the attackers seek information about the company's next generation of devices, let's say, so the next Pixel phone. So that involves obtaining planning documents, design documents, timeline, pictures, schematics, etc. And the third scenario is an attacker going after the AI work that's being done at Google. So basically, the attackers are seeking information on the next generation of AI. So that's unpublished papers, model weights, code, etc. All right. So here's the operational setup. For those attacks, we have 15 participants who are all full-time employees with interest in cybersecurity. So most of them were software engineers, and all of them were familiar with internal tools and information storage practices and systems. So we asked these volunteers to try to access sensitive information outside of their normal area of work. And that really is meant to mimic real-world insider threat scenarios. Participants were instructed to choose and emulate a profile from one of those playbooks that we provided them. One thing that I forgot to mention is that those playbooks are relatively vague in what to do. Really, we wanted to give participants the opportunity to, in some sense, go wild and perform all the actions that they could think of. And I would say that there were various levels of success for the participants. Some participants were very successful or more successful than others, let's say, but also some scenarios, some playbooks were a lot harder or a lot easier to execute. All right. So here are the evaluation results. So as Ellie mentioned, we have about 180,000 full-time employees. And for this particular evaluation, we chose a triaging budget. So let's say you have analysts, and you're going to give your analysts a certain amount of work per day. And here, we're just triaging at the top 10 users per day. And the main evaluation here, the main evaluation results, is that we detect 4 out of the 15 attackers. This is quite a hard evaluation, so 4 might not seem like much. However, I also do want to mention that the precision here is what we're optimizing for. So if you were to triage more than 10 users, you would obviously get more of the attackers. But we're really focusing on the very low false positive rate. There are significantly more details and more evaluation numbers in the archive paper that's available online. One thing I want to give to you before we end this talk is a reference to the reference implementation that's now live on GitHub. So this is a reference implementation. I want to be very clear about this. And Facade is really meant to work on large-scale data sets. And you would have to do your own featurization work, essentially, even though Facade provides facilities, as we previously saw. We do not believe that using Facade on a small-scale data set is necessarily appropriate, but it might work, nonetheless. So here are the key takeaways for our talk. Insider threats are low-incidence, high-impact attacks. They do require deep contextual analysis and understanding for detection and explanation as well. We presented Facade, which is a high-precision contextual anomaly detection system. And Facade works both for single accesses and for scoring entire sets, entire time windows of activities. Finally, I hope I could give you a clear sense that Facade is adaptable to many systems and use cases because of how general the user and resource representations are. And we're also providing a reference open source model and featurizer code. And with this is our last slide. Thank you very much for your attention. Here we have the QR code again for the slides, and the code again is available on GitHub. We're happy to take any questions you might have in the second room after this talk. Thank you.